Welcome to qnawire.
Okay, so our first molecule is diethyl ether, right? Drawn like this in bond line drawing, which is equivalent to CH3, CH2, bonded to O, bonded to CH2, bonded to CH3. But we also know that this oxygen has two lone pairs, right? So in fact, this ends up being very similar to water, right? And essentially, we know that the dipole for a lone pair is going to be much bigger and stronger than the dipole between oxygen and carbon. But nevertheless, it's very similar to water, in which we get a net dipole, which points in the direction of the lone pairs, right? Maybe I'll draw the net dipole in a different color. Something like that. Okay. Our next molecule is CO2, which looks something like this, right? So in bond line form, this would be C, doubly bound to O, doubly bound to C. Nope, that's not right at all. Sorry. Got this backwards. This would be O, C, O, right? That is O, doubly bound to C, doubly bound to O. This is CO2 with two lone pairs on each oxygen. Okay, and so you'll notice the only dipoles that are going to exist are between carbon and oxygen, and they are going to point at oxygen, one to the left and one to the right. And this drawing is accurate in the sense that CO2 is a linear molecule. There's no bends, right? We've got a carbon with a double bond to the left and a double bond to the right, right? So it's got two electron regions, right? So its molecular geometry and its electron geometry are linear. And if it's linear, and these oxygens are basically pointing in opposite directions, or the dipoles to them are pointing in opposite directions, that means that they are going to cancel out. There is no net dipole to CO2. There are bond dipoles, but those bond dipoles are in equal magnitude and facing in opposite directions, giving a net dipole of 0.